Hey everybody, today we are going to talk about exponential functions. And we want to start with the definition of what it means to be an exponential function. You might be tempted to think that, well, if there's an exponent in a function, then it's exponential. Well, we've been dealing with lots of polynomials that had exponents, but none of them had an exponent variable. So that's where the difference lies, is when you start throwing variables into the exponent, that's when we start dealing with exponential functions. And we try and really keep a narrow definition of an exponential function so that they all have similar characteristics and behavior that we can kind of rely on. So our definition of an exponential function is going to be any function that can be written as f of x equals some number a, some non-zero real number a, times a number b to the x. And sometimes we call that a the initial value, which we'll see why as we start playing around with these. And some restrictions on the b is it's got to be a positive number. And so you won't see a base that's negative with your on your exponent. And b cannot equal 1. That would be a pretty boring function. So we exclude any functions where b equals 1. Okay, so let's play around with these a little bit and see what we can do with them. So one thing we might be asked to do is find the equation of an exponential function when you're given just 2 points. Usually one of those points is going to be the y-intercept like we have here. So if I have 0, 3 as one point and 0.2 3/4 is the second, let's see if we can come up with the equation for this exponential function. So I'm going to start with that basic definition, a times b to the x, and I'm going to plug in the y-intercept first. When you have a 0 in there, it usually helps to eliminate one of the variables because I do have 2 I need to find. I need to find a and b to find this function. So I'm going to plug in 0 for x and 3 for f of x in the function. So I have 3 equals a times b to the 0. And well, b to the 0 is going to be 1 no matter what b is. So I end up with just a equals 3. So I found my initial value a. And I know my function looks something like this now. F of x equals 3 times b to the x. And so now I have the second point to find that last value, the b. So I'm going to plug in 2 for x and 3/4 for f of x into the function. And now we can solve for b. So 3/4 equals 3 times b squared. I'm going to divide by 3 on both sides to get the b squared by itself. And so the 3's are going to cancel. I end up with 1/4 equals b squared. If I take the square root of both sides of this equation, remembering that b has to be positive, I know that b equals 1/2. And the negative 1/2 does not work because that would give me a negative b, which is not an exponential function. All right, so I found a and b now, and I've got my equation. F of x equals 3 times 1/2 to the x power. So if I'm given 2 points, particularly one of them being the y-intercept, I can use this method to find the equation. If I'm given a graph with 2 points pointed out, I can do the same thing as well. One of the applications that we often see with exponents and exponential functions is interest. Now, interest occurs usually in like a loan type situation or maybe a credit card where you're borrowing money and you have to pay interest on top of it for the privilege of borrowing that money. Now, oftentimes interest is compounded so many times per year. And so this equation will tell me how much money has accrued. If it's a loan, it's how much money you owe. If it's like a savings account, it's how much money you've earned. And so the A is the amount of money accrued, or sometimes called the future value. P is the principal, so that's the amount of money you started out with, the amount of money you borrowed or the amount of money you invested into a savings account, for instance. And this is sometimes called the present value. So if you see any of those terms, that's what they're talking about. R is going to be the interest rate, and make sure usually you're given that interest rate in a percentage. You got to convert that to a decimal when you're using this formula, or the calculation will not come out correctly. And N is the number of times compounded each year. So what happens when interest is compounded is they take any interest that has occurred during that period and they add it back to the principal, and then it starts accruing interest. So if it's money that you owe, then that interest, every time they compound, the interest that's been accruing during that period gets added to the principal, and now you're paying interest on that interest. So it compounds itself. And the same would go for a savings account. So you might see something that's compounded once a year, or maybe it's monthly. So N would be 12 in that case. If it's biannually, that's twice per year. So N would be 2. So it can really vary depending on the problem. So keep an eye out for that on the N. And of course, the last variable, which I actually forgot to list here, is the T, which is the amount of time in years that the loan is going for. So let's look at some examples to see how we might use this formula to calculate the amount accrued or compound interest. So the question asks, find the amount of money accrued on an initial investment of $2,000 after 3 years, compounding monthly at a rate of 2.5%. So they gave me a ton of information there. First of all, they told me it's compounding, so automatically I know I'm using this compound interest formula. They want me to find the amount, so that's going to be the A. And so the first thing I'm going to do is I'm going to take all these numbers they gave me and I'm going to assign them to the appropriate variable, so I plug them into the right spot in the formula. So the $2,000 is my initial investment. That's the principal. The time is 3 years. It's compounded monthly, so N is going to be 12 for 12 months. And that 2.5%, if I convert that to a decimal, I'm dividing by 100, so I get 0.025 for the rate. So I'm going to take all of that and plug it into the interest formula, and it will look something like this. A equals 2,000 times the quantity 1 plus 0.025 over 12, all raised to the 12 times 3. One of the trickiest things is getting all this plugged into your calculator correctly. If you can do some of it separately, you can. You can plug this all in at once. Just make sure you're using parentheses appropriately. I've got parentheses around the 1 plus 0.025 over 12. If you're going to do 12 times 3 typed into your calculator, you're going to want to put parentheses around that, or make sure that it's all being put into the exponent and not just the first of the two numbers. If you plug all that in, you should get some large number with a decimal at the end. This is accruing. You should get something greater than what you started with. So keep that in mind. So make sure you're getting realistic numbers. If I got like $100 from this, then I know I did something wrong because it should be greater than the 2,000 that we initially invested. So you should get approximately $2,155.60 for this one. You do round off at the hundredths place when dealing with money, so I rounded off at that second decimal there. So definitely practice plugging this into a calculator. You don't want the calculator and the technology aspect of this to be the thing that trips you up when doing problems like this on a test. Another application of exponential functions is continuous growth and decay. So this is pretty much the same formula that we started with, a general exponential, but we've got a couple of extra variables, and each variable has a very specific meaning here. So A of t is equal to A times e to the RT. So A is the initial value again. R is what we call the growth rate. And if it's growing, R will be positive. If it's decaying or decreasing, it would be a negative value. T is the time elapsed. And E is a specific number. It's an irrational number, kind of like pi, that we'll talk about more in class, that you would use here. It is a constant. You will find it on your calculator. Now, going back to interest for a second, you can compound interest continuously. The more often you compound, like you could compound daily, and then N would be 365 days. If you want to maximize your compounding to the greatest possible amount of compounding, we call that continuously compounded, and we end up with this formula very similar to the growth and decay, where we just change the letters because they mean something different in this context. So P is the principal again, E is that number E, and then R times T is the rate and the time, just like with the compound interest formula. So if you see a problem that says continuously compounded, use this formula instead of the other compound interest formula.